Okay, so why don't we get started? Can I request the panelists to please come on stage and take their rightful positions in the podium? So we are very honored to have Dr. Anant Sahai, who has agreed to serve as the moderator of this panel. So I'm going to hand it over to him. Anant.
Okay, great. Does this work? Yeah. Okay. Let's see. So everyone sit down. So what I thought I'd do is I'll start, then I'll introduce the other panelists one at a time, sort of they can give a little bit of information for everybody. And then hopefully this will be a very interactive conversation. We'll have a little bit of, I'll ask them a few questions at the beginning just to kind of get things started, but then really I want everyone else to join in the conversation. So, the topic for this panel is really about privacy. And I think, having participated in many such conversations before, I think privacy is something that we all have lots of intuitions about and lots of technical as well as societal implications. And one of the most insightful comments that I've ever heard about kind of framing the conversation about privacy really came from Stephen Wicker from Cornell. And so maybe I'll just take this mask off. So I want to just relay his argument, which I think that really is thought-provoking. So he argued that when we think about privacy, privacy exists in a societal context, and it's not tied just to information-theoretic properties of the data alone, although that's definitely something that is important. And the argument he used was a thought experiment that went like this. He said, suppose that there was a public square out in the open, and you put a mirror in the public square. Have you violated anyone's privacy or sense of decency or anything? And the answer is no. No one thinks that this has violated anybody's anything. And he says, okay, what if I put that same mirror and I put next to it a pile of sand and some books on human anatomy and biomechanics? Have I violated anyone's privacy? And the answer is no, I have not. He says, well, now what if I take the mirror and I replace it with a video camera and a giant display that acts like a mirror, as well as I take the sand and I replace that with a computer, as well as books on biomechanics and human anatomy that have now been moved electronically. Have I violated anyone's privacy? And the answer is still no. And then he said, now let's take the next step. I'm going to take the camera, I'll take the knowledge of biomechanics and human anatomy, I'll program it in the computer, and I'll have a computer graphic system that takes the pictures of everybody as they walk by and renders them without any clothes on as they walk by. Are people going to feel violated now? And the answer is yes. And the comment is, well, the information theoretically, nothing has changed. I have not used any additional information that was present before, and I've caused a violation to happen. And this is just meant to help people kind of take into your minds the idea that when we think about privacy, it's in our intuitions tied also to very deep human intuitions of modesty, actually. Kind of deep, it connects into those. And so conversations around privacy naturally are interdisciplinary and have to include all of these different considerations. So I just want to put that out as a kind of, nothing there is due to me. Everything's due to Stephen Wicker's argument, but I thought it was just worth repeating as an argument. And so with that, I want to introduce other people to kind of give you a little bit more technical perspective here. And I'll start with Stratis on that end of the room. So Stratis Ioannidis is a professor here at Northeastern, associate professor. He works in machine learning and privacy from both the deeply theoretical as well as practical perspective. And so take it away.
Hi, everybody. So we thought as a panel that it might be a good idea to give a brief introduction on privacy-preserving technologies for data analysis, just to give context to the discussion that we will be having. For this purpose, I'll say a few things. Let's see if this is going to work. Okay. So just as a sort of lightning 5-mile above the ground review and overview of what how privacy is perceived from an algorithmic and theoretic point of view. I'll say a few things about information-theoretic privacy, differential privacy, and also secure function evaluation and secure multi-party computation. So starting from an information-theoretic point of view, think that you have a setting where you're going to release some data X that may or may not be private, okay? But somehow that data is correlated to some variable Y that you deem private through some joint distribution PXY. So normally you wouldn't mind releasing X, but if you do, if an attacker has side information in particular, knows something about this joint distribution between X and Y, they may be able to infer the private variable that you would mind having been released. So typically how this is approached from privacy-preserving techniques against statistical inference is that rather than releasing your actual X, the actual data that you don't mind sharing, you share a perturbed version that has been distorted in some way so that it becomes decorrelated from your private variable Y, okay? So perhaps by minimizing the mutual information subject to some distortion constraint. And actually, before I move on from this, one problem with this is that, to implement things like this, you need to know the joint distribution. It's also a little bit hard to scale as a plan if the distributions that you have if the variables that you have are highly dimensional. And moreover, it could be quite strict because if Y is very correlated with X, then you may as well produce noise and not report anything at all. An alternative approach, which is also the industry standard in some sense, is differential privacy. So rather than worrying about things of that nature, we assume that we have some kind of trusted evaluator that is going to compute a function over some data and then release this function out to the open, publicly. And now this function is differentially private if the potentially randomized output changes very differently if you perturb and you change the input of any one of the individuals that participated in this computation. Okay, so the distribution of the output changes very little if we change only one entry in the table that came from the users. This is weaker than the notion that we discussed before, in the sense that we don't mind exactly about what is being released about the individuals in the database, but we have some sort of plausible deniability in the sense that even if they participate in the database or not, the outcome would not be very different. And perhaps a quintessential example is doing a study and understanding what is the probability of getting cancer if you're a smoker. So if you release this information, an attacker that has additional side information about whether you smoke or not will be able to tell the probability that you get cancer. But whether you participate in the study or not, that will not affect this process. Okay, and so this is the industry standard in some sense. This has been a very successful theoretical definition. It has led to a lot of research. Many algorithms that we care about applying on data have been made differentially private. This is done by adding noise either at the end or at strategic points throughout the algorithmic process of running some algorithm on the data. And it's also, there are a lot of real-world deployments. So the US Census Bureau uses this. Many companies such as Google and LinkedIn and so forth use this for releasing data, but they also use this internally for releasing data from one team to another, okay? Now, and finally, to wrap up, in terms of techniques, secure function evaluation and secure multiparty computation work somewhat differently. Now the evaluator is not trusted. You have some data, you want to give it to the evaluator, and the evaluator will compute a function and will learn just the function and nothing but the function. So I drew this as if the users are sending the data in an encrypted form, but the way that usually this happens is that the evaluator engages in some kind of cryptographic protocol of information exchange with the users, and somehow in the end, they learn F, evaluate on the data, but nothing more. This is also, there are main techniques for this, from Yao's garbage circuits, homomorphic encryption. They differ on the type of assumptions that one makes, and they also differ on the type of functions that you can compute. But nevertheless, this has also been this predates differential privacy. It's also a very successful agenda in terms of algorithms that are computing this, and there are also presently tools that one could use in order to securely evaluate a function over private data for a variety of tasks. And I should point out that the challenge here is computational. The cost of computing a function in a secure way, because it involves crypto, is much, much more expensive. The barrier keeps being pushed, and we are able to compute bigger and bigger things, but we're nowhere near the hexabytes that Falco Dressler presented in the morning, let's say. And I'll stop here.
Thank you. Next, we'll have Dola Saha from Albany. She's an assistant professor who has worked on machine learning for wireless communication, has many results in that area.
Sure, thank you. I don't have any slides, but I would like to talk a little bit about what is RF data. And so RF data can be of different kinds depending on what is the application that we are looking for or looking at. And if we are looking at different applications, we would require different kinds of RF data. So when we are looking at RF data, where are we collecting the data? Is it somewhere that is collected over the air, like an eavesdropper collects data? Is that any useful data? Or is it going to be somewhere that is very close to where it is being transmitted, or where the transmitter antenna is? Or should it be at the baseband? And oftentimes, I would like to look back at what image community and video community has done, because they have been ahead of the wireless community in terms of the data. In video or image, one can take the image and can label those data. For wireless, we cannot do that, because oftentimes the data needs to have that metadata information which actually captures all the RF environment. And that is the ground truth for us. For example, if we are looking at waveforms and that waveform is hidden under the noise, we cannot look at the receiver side and say that, well, this is what has been transmitted. So a lot of the data that can be captured at the eavesdropper's point of view is almost useless in many wireless scenarios. So for us, we have to look for data that we know has been transmitted. And moving towards that scenario, even when you're looking at channel estimation, so you need to know what exact bits has been transmitted, because no one knows the ground truth about the channel at that point in time. So whatever we are predicting in terms of AI and machine learning algorithm, it has to know whether the BER curve has moved at all or not. If we move a little bit towards higher up, even still in physical layer, if you're looking at multiple antennas, so what coding techniques have been used? If you're looking at channel coding, what bits have been transmitted? So those are the important questions or important parameters that are required, without which we cannot run any AI ML algorithms at the receiver side. On top of that, we are trying to work on several algorithms that do end-to-end learning, meaning transmitter to receiver learning. So in those cases, we need data where what has been transmitted we need to know. We need to know the channel, instantaneous channel, as well as the receiver side, to do any kind of algorithm that can do the differential algorithm on the channel side of things. So overall, I think privacy is something that we have to look at from a different perspective than what image community has looked at, because we need to have the transmitted information inbuilt within the transmission itself. And to me, it's also very surprising to see how much people, public, actually put out their information in public. For example, if you take a look at social media, that has changed how people are putting out their information. So when I'm looking at that community, and people have been doing a lot of data analytics on social media, my question is, why can't wireless community put out a test bed where we say that, well, this is the cellular data that they are going to, where people are going to get connection, but we are going to collect that data. And that should be real experimentation. That should not be anything, that should be something like AT&T's help and require cellular infrastructure, where we have to be able to say that, well, you better not transmit your bank ID or any information like that, because you are now in that zone, just like our National Radio Dynamic Zone. Here, this will be a privacy zone where you can do whatever you want. We are going to give you internet access, but your data will be collected. And that will be true data, true RF environment. And why that will be useful for us is we can do a lot of experiments, lot of events that we can track. For example, it can be simple as Boston Marathon, or it can be the president visiting some place, and how wireless data changes in these times. Those are real experiments that we can do if we have this kind of an enclave. So.
Okay, thank you very much. Finally, on the panel, just to get things started, we have Charles Schroeder, who you've already had seen from National Instruments. You met him in the morning session, and he has a very broad base of experience with NI with radio-related technologies as well as beyond.
Thank you. I wonder why all the panelists got as far away from the moderator as we could. I'm gonna build on what you just said about wireless being different than imaging, and I'm gonna take a little bit of a non-theoretical opinion and go more towards our responsibility as a community to educate the lawmakers and the government authorities to provide frameworks for us to operate in. You take imaging, and you're right, with social media, there are so many images. I don't know what privacy means in social media anywhere anymore. You take a look at the paparazzi, and the paparazzi can basically invade your privacy under the freedom of the press moniker. You take a look at Google. So Google's got these Street View things, and while they do take an effort to blur out faces and license plates, there was a lawsuit in the UK not too many years ago about a guy who came out of a store he probably should not have been in, and his wife recognized his clothing and sued, and was the case was thrown out. That okay, you shouldn't have been in there. I mean, you're not protected under that scenario. And yet, in the wireless world, we don't think about those things the same way. I'm not a lawyer, but if you look at things like the Electronic Communication and Privacy Act in 1986, sort of equated snooping on a wireless transmission as eavesdropping. And think about in 1986, how many of us had Wi-Fi or a cell phone? I mean, that's 36 years ago, and yet Google just lost a $13 million lawsuit just because they had an antenna on, it may have been more than that, but my initial web reading is because they had an antenna and were capturing waveforms. And so the climate is such that we think about communications and privacy different than we think about images or other forms of data. And there is a society and a government and a lawmaking piece of that as a scientist, I just want to say, hey, look, I'm not going to do anything bad. Just let me have the data, and I can build amazing things that are going to help with the communications of the world. But that's not necessarily the full environment. And I think it is part of our responsibility to help build trust and to build education so that we can get a legal and societal environment that wants to trust scientists with something as little bit scary for some people is artificial intelligence, because you start putting wireless and artificial intelligence together, and you could mentally create a scenario which is much scarier than I think any of us are thinking about when it comes to privacy.
Thank you very much. So what I'd like to do next is I'll ask a couple of questions. Just a question to each panelist to kind of help get maybe some more thoughts flowing. I'll then encourage, panelists, if you have questions to ask each other, we can, or me, we can do that. And then I'll kind of open it up to everybody. So I'll just start kind of with a basic question for Stratis. From your perspective, the tools that have been developed by the, let's say, the homomorphic encryption, the obfuscation, the differential privacy, and information-theoretic privacy, that community, how usable are they for researchers who are outside that field? I know we've seen, for example, in AI/ML have a big impetus that kind of lowered the learning curve for people to sort of get in to try stuff out by the ease of use of tools like PyTorch and so on. What's that situation like in the privacy-preserving tools?
Yeah, so there's a very big effort to make these things as available as libraries that one could potentially use to write an algorithm in a high-level language, not even worry about any basic knowledge of crypto or how to tune noise added or anything like this, and then take the program that has been written in this high-level language, parse it, and then do what needs to be done. and I put some links on the slides on such tools, mostly from the crypto point of view, but these things also exist for differential privacy. So there's a push towards that automation. Now, how, I mean, let's say the motivation is there to make these things as non-opaque as possible and usable. On the other hand, whether one of these will be adopted in the next couple of days and in the next couple of years and be as available as PyTorch, I don't know. I don't know if this is going to be such a success. One aspect about this is also because the goal is moving, and these things are becoming also better, and more efficient. So some things become obsolete, and things are moving both from the software side and the hardware side as new hardware is released that can do this particular cryptographic primitive very efficiently. The library that you were using before and the tool that you had maybe is now obsolete, and it's better to move to something else. So at some point, I'm guessing things might stabilize and that might become a reality.
Yeah, thank you. For Dola, the question I have is, we saw in the morning that people brought up the idea of synthetic data sets, where you kind of take real data, learn from it, find a way of synthesizing data as a way of kind of doing privacy in a general sense, because the synthetic data is just purely synthetic from an algorithm. How do you think about that in the wireless context?
So that's a very good question, because I think that there are two parts to it. One is, how do we capture the data, or where do we get the data when we are actually looking at it from the experimental, true real-world data? And real-world data, if we are sniffing, and the reason why I'm saying sniffing, because then I don't know what bits are transmitted, because we can get some parts of it, but it's not guaranteed that I know everything that has been transmitted. So I do not know what is the algorithm that I'm going to do is going to be enough or not. So moving that over there captures might not be useful for many wireless applications, in my opinion. Some of the applications are fine, like what's the current usage, what's the traffic pattern, all of those are fine, where we can identify the amount of spectrum usage. But if you're looking at RF applications, for example, fingerprinting, if you're looking at covert communication, if you were looking so how do you verify whether what you have moved from experimental version or real world data to a synthetic data is that correct data, or how much you can extend or how much you can extrapolate. So that's, I think, one of the bigger question that we have to answer as well.
Yeah, thank you. Charles, you raised a very good, interesting point about, that there's a matter here of perception. I'm very curious, to what extent do you think that a culture or a feeling of risk aversion on the part of people who approve things is part of the blame? I remember in the morning conversation, there was a lot of, just don't do it kind of coming out, which, how much do you think is a problem of the laws actually being prohibiting things and people being conservative in the face of law, of saying, I don't want to get anywhere close to a problem, so I don't want this headache?
Yeah, so I'm about to say probably the most controversial thing that I could possibly say at this conference, which is I think the government is actually reasonable. Mm-hmm. We had a scenario I'm going back to the automotive space, but this is an entirely different case. When you're testing an automotive radar sensor and you want to be sure that it can detect all of the objects in the real world, the correct way to do that is do as much as you can in simulation. But eventually, before you do a drive test and risk hurting somebody, you put it in what's called a hardware in the loop system, where you will electronically spoof, if you will. It's the wrong word, but you will emulate targets, and you can detect, is that a bag blowing across the front of the vehicle? I should just keep going so I don't get rear-ended, or no, that's actually a small child on a bicycle and you hit the brakes, so you don't worry about being rear-ended. The problem is we ran into a system called DERFM, and DERFM is a military term for spoofing targets for a radar, and that's highly illegal. Legal is maybe the wrong term. Highly discouraged. Like, you can get in a lot of trouble for DERFM. Used to be a bad word. You said DERFM in public and you'd worry, you'd watch the exits. And we went and we said, okay, look, we've got a choice. We can say that every spoofing a radar target electronically is bad and evil, and we should just live with bad cars, or we do this. And we had a very good discussion with compliance, and it led to a set of clarifications in the ruling that said, in these frequency bands for these purposes, this is an allowable technique. We need this for the safety of the population. It's in people's interest. But you had to get, to your point, you had to get over government will never allow DERFM. I mean, you just can't do that. And so we had to get over it. We had to spend the time to collect the data, to build some consortium and some people that were trusted and represented, and build a community, and then come with a well-articulated case of exactly what we were doing, what we're asking for. And actually, once we did that, it was reasonably simple to get a clarification in what was not allowed and what was allowed. And I think the same thing might be true for us. If we can be clear about what we're trying to do, we can be clear about the use cases. Your point, synthetic data for RF fingerprinting makes no sense. No sense whatsoever. We are doing our best to use different types of encryption to preserve people. That we should not put up our own mental blocks that everything is bad until somebody gives us permission to do it. At the same time, I don't think we should be running afoul of laws. You need to respect the laws in whatever geography you're in, but let's be proactive and not assume that the government won't move, and let's help them make good policy.
Okay, thank you. Okay, so if there's questions that you want to ask each other, I think you can also just signal to me that you want to ask, and otherwise I'll also invite people to come in and sort of join the conversation. I would like this to be a conversation not just with the panel, among the panel, but also among folks in the audience. The collected expertise here is more, and hopefully this will help seed what goes into the breakouts, where it really is a group of peers talking. So yeah, Manisha.
Dola, I want to ask you a little bit more about when you say you need the baseband data, right, for what you're doing. You don't need to know the bits that were transmitted. You need to know, say, for channel information, most signals have preambles. You could decode the preambles and get most of what you want from the channel from the preambles. I'm sure all of us have used Wireshark, and we're grabbing signals off the air. We're not decoding down to bits. And I think the example that you mentioned about Google, they were actually decoding messages. They were actually taking encrypted Wi-Fi off the air and decoding down to what people were sending to each other in terms of what they were searching for. That, I think, definitely crosses a boundary as to what. And I think as a community, we haven't made that very clear to people that, what we want. We don't really care what you're saying to each other. All we care is what the signal looks like. And I think we can do a better job of explaining, what it is we are collecting and why we are collecting it. So for example, Intel has these cards, Wi-Fi cards, where you can get the channel information out from the card itself. We're not looking at the data. We're not looking at the bits. We can get the channel information very easily. Pretty much, if you take an SDR and the control channel information that he mentioned, is it really that difficult to explain to people that we are not decoding your messages? We're just looking at RF energy. And if not, how do we do it as a community? It's probably something we should think about a little bit more.
So to answer to that question, if we are trying to do channel estimation in terms of better channel estimation, what we can do is we can always try to go as low as like 4 dB, 5 dB, and see what linear estimation is doing. Now, or whatever signal processing based estimation is giving us. Now, whether we are doing a better estimation or not, there is no ground truth. If I'm working on simulation, MATLAB gives me that this is the exact channel. On the other hand, what we can show for channel measurement, better channel estimation and equalization perspective, is we can do the best algorithm that AI/ML can do, and we show that BER curve is moving. So that's the only way when we are looking at channel estimation. So if we are trying to do better channel estimation, we have to show that we are doing better only by showing that BER curve has moved. So that's one of the applications. Another application, if you're doing an RF fingerprinting. So what has been, or like at a very low SNR level, if we want something to work and see, then if we are looking at something that is being transmitted already, then there is hardware impairment as well as channel coming into play. And we cannot differentiate which one is what, or which one is corresponding to that error. So for that, we also need the baseband channel information. If we are looking at, for example, another application I would say is channel coding. So for channel coding, what if we are doing end-to-end channel coding or end-to-end system, we need the channel in between, which is a channel model, which is differentiable for the back propagation to go back. So for that as well, we need to work on, if we are working on real data, we need the bits, right? So without the bits, we don't know whether we are making an improvement or not.
So
can you not do a proxy, let's say mean squared error instead of the bits?
So
yeah, I'm just wondering whether, I mean, I know that's a very specific example, and maybe for that you do need the bits, but you can look at things like in the preamble where there is no, of most signals, there is no information. So the control channels, there are bits in there, but there is no user specific information in there. And so I think, we can try to sort of meet this problem halfway and say, okay, we do need the bits, but maybe we'll look at the bits where there is no user information and try to do it that way.
So I think to follow a little bit, just to engage in the conversation with Manisha, what you're saying, I think, and also what Charles was saying, one of the things that definitely exists in human life socially, right? And anyone who lives in a, other than an isolated rural environment, is that people know not to look, or not to hear or not to listen, even though someone is having a conversation here and you can hear it, you're also not hearing it. Like you exercise this human respect for others by ignoring information.